All right, Chem 11. Our next topic in the solutions unit, acids and bases. And I know we have a little bit of pre-exposure to this topic from grade 10 science, so that'll be good to have with us. Same format as usual. Our notes from the D2L page that we would normally use in class are right here on the iPad, and then I've got the whiteboard surface to add some additional information or a diagram or a calculation, whatever it may be. All right, so let's start our lecture. The first slide here talks about the differences and similarities between acids and bases, right? So it's almost set up like a T-chart here. Litmus. Litmus is an indicator of pH. So litmus helps tell you if something is acidic or if it's basic. Acids turn litmus red and bases turn litmus blue. Just think bases blue, BB, right? And that's why I actually use those colors in my title, the red and the blue. And so litmus will respond to different substances, and if it turns red, you know that it has acidic properties. If it turns blue, you know it has basic properties. Acids taste sour. Candies like Sour Patch Kids and such, they have citric acid in them, ascorbic acid in them. This is what gives them that sour taste, right? Bases taste bitter, right? Baking soda is a base, and if you ever taste baking soda, it is quite bitter, right? We use a lot more acids in our foods, you know, as far as taste goes, a lot more acids in our foods than we do bases. In the lab, of course, we would never taste either of these things. You know, we don't taste any chemicals in the lab, but just when we do use them in foods, that's the taste that they give. Acids, if the acid is half decently strong and it pours on your skin, I said here it feels burny. What it does, it's a burning irritation type of sensation that you'll feel on your hand. Bases, on the other hand, feel quite slippery. Bases are very, very slick, like oil, when they pour, you know, when you feel them on your skin. Now, in the lab, we use weaker acids and bases because they still get the job done. We don't use the highly concentrated stuff. We dilute it down. Little shout out to last lecture. But we dilute them down, and sometimes some base will get on something, and I'll tell the students, you know, you can touch it. Make sure you rinse your hand right after, but you can feel the slickness of a base, very slippery. Both of them can cause damage. They're both highly reactive. So they'll be highly reactive with other chemicals, and they can be highly reactive with your own flesh. So if you do get a strong acid or base on your hand or on your skin or in your eyes, it can start to react with your tissues and basically destroy them on contact. So we don't want to get any of that on us for sure. Both of them are water soluble. So both of them can be added to water and they mix in there perfectly. They have no problem doing that. Both tend to be ionic compounds. You know, if you remember, an ionic compound is a metal and a non-metal, or it's a metal and one of the polyatomics, or it might be something has polar properties because of the differential between the electronegativity. So there are some bases that have no metals in them, right? They might have one of the polyatomic ions in there, and if you remember, they have no metals in them. Or it can be something like ammonia, which is polar, so it's NH3, so it's a polar covalent compound, but when it reacts, it absorbs ions, so it's kind of like an ionic compound. All acids start with H. Right? And we'll see why in a second. So every formula of an acid, it usually starts with H. The common acids that we use in the lab anyway. Bases, there's no one catch-all rule here. A lot of the bases that we would use though in the lab end in OH. All right, hydroxide. So a lot of our acids, they start with H. So it's H something. And bases in the lab tend to end in OH, but not all of them. This is not, see, acids begin with H. Bases may end with OH, so not all. I'll put that in there as a little reminder. All right? And all acids definitely have the hydrogen. So, in terms of identifying an acid and a base, there were two theories. The first one was put forward by Svante Arrhenius, and it's called the Arrhenius theory of acids and bases. Svante Arrhenius was a Nobel Prize winner in 1903. Yes, the Nobel Prizes have been given out for well over 100 years. And his Nobel Prize was in the field of chemistry, go figure, for his work with solutions. Excuse me. And basically what he said an acid is a substance that produces H plus ions in water. Now, if we look at a hydrogen, right, because H plus, H is hydrogen. If I look at a hydrogen atom, all right, what is it? Well, its atomic number is 1, which means there's a proton. Its atomic mass is also 1, so it means the only thing in the nucleus is that proton. And if we're looking at an atom, there's 1 electron, because of course in an atom your protons and neutrons cancel out. There's the same, they have the same number. So a hydrogen ion, it will lose this electron, and a hydrogen ion is simply what? It's simply the proton, right? So a hydrogen ion is the same as saying a proton. And I just spelled proton wrong. Wow. So hydrogen ion is simply a proton. And so you'll see it like this. You'll see it like this, right? Sometimes I write P with a plus for it. Or proton now can be that. All right? So 3 different ways. How we'll be representing them in this unit, the solutions unit, we'll be using the H plus here. So when I throw an acid in water, right? I throw that acid in water, and what I'm going to find is, making the sound effects of my, right? So if I put an acid in water, I end up with a whole bunch of these in there. Now, Arrhenius said a base. If I put a base in water, a base will dissolve and produce OHs. And OHs have that 1 minus charge, so there'll be a whole bunch of these floating around in there. All right? Now, here's the problem, right? He said the thing's going to, dissolve and it's going to produce these OHs. And we know that a lot of bases have OH at the end. Sodium hydroxide, lithium hydroxide, calcium hydroxide. So there will be OHs, but not everything has that OH, right? All the acids started with H, and OH was in many bases. But there was a problem with this, right? The problem with his theory, and I'll put the blue OH down here for the base, just like we got the red one for the acid. The problem with this theory is that there was a group of salts that acted as acids or bases when they were dissolved in water. And the salt didn't have an OH in it, right? A good example of one of these ones that causes a problem, right, is sodium carbonate. Sodium carbonate acts like a base, right? But there's no OH in there. There's an O, but there's no H. So I can't make these based on that alone, right? Another one. Ammonia is a base. You learned probably about ammonia being a base in grade 10. There's lots of H, but there's no O in the ammonia. So that was the problem when he said they were parts of the, when he said all acids begin with H and bases make the OH, it wasn't quite exact. He didn't cover everything. We know that a salt, like this one, is a simple ionic compound. It's got a positive and negative ion. The sodiums are positive. The carbonate is a negative polyatomic ion, right? And they don't contain hydrogen, like this one has no hydrogen, this one has no oxygen. Or they don't have an OH at all in their formula. So his theory was accepted at the time, but then later discarded, right? And of course, Svante Arrhenius, this handsome looking fella here, he quietly plotted his revenge for several years in the chem lab. Anyway, he actually died in 1927 before any revenge could be exacted. Okay, so we'll move on to our second theory. Now, this is the accepted theory. This is the Bronsted Lowry theory, and this is two gentlemen in chemistry. And they were similar to Arrhenius in their explanation, but not exactly the same. All right, and you'll see what I'm talking about here. So you have Johannes Bronsted and Thomas Lowry. They came up with a better way of describing acids and bases in 1923, right? And what they said was an acid was anything that when you dump it into water, it produces these. So it can produce hydrogen ions. Well, that's very similar to Arrhenius. In fact, it's pretty much exactly the same as Arrhenius. Acids give away protons because we know a hydrogen ion is a proton. So acids produce protons and they can go and join other things, right? If protons were money, you'd love acids because they go around just throwing out money all the time, right? A good acid gives off lots of protons. So protons are $5 bills or $10 bills. An acid would walk down the hallway giving everybody $5 or $10, right? A base, and this is the main difference. A base is any molecule or ion that can combine or accept hydrogen ions. So there's a difference here. That OH thing is gone, right? It takes a hydrogen ion or a proton and it accepts them, right? The acid is the proton donor. It gives off, right? If you're an organ donor, you're giving off, your organs after you pass. Here, someone can use my liver, someone can use my heart, whatever. So acids are proton donors. Arrhenius agreed. This is the part that is new. Bronsted Lowry, their theory says bases are proton acceptors, right? They're proton acceptors. So it has nothing to do with the OH. And so that actually makes sense because if I look at something now like ammonia, right? Ammonia we said was a base, but it didn't have the OH thing. Ammonia will accept a proton and it will form ammonium. We know ammonium because it's on our polyatomic table, right? So it accepts a proton. This is a base. And of course, if you do a pH test, it will be above 7 if you remember the pH scale. We'll go over it shortly, but if you remember that pH scale from grade 10. This is a more accurate way of describing them. So there's Bronsted there, very happy looking gentleman, and he said an acid is a proton donor. And there's Lowry. A base is a proton acceptor. So one gives off the protons, the acid, and one takes them in and accepts them and incorporates them into their structure. The base is the proton acceptor. Now, here's something that gives people some problems, but I think there's a really easy way of explaining it, so we'll give it a try here. So according to Bronsted Lowry, they said every acid has a corresponding base and every base has a corresponding acid. What the heck do they mean by that? So let's take a look. What exactly? So basically, when an acid donates its proton, its leftovers are now capable of taking that proton back. And a base, right? The base will accept the proton, but it's always capable of giving the proton back. So if you think about it, the acid gives off the proton, but can then take it back and accept it So the acid gives it off, which makes it an acid, but then it takes it back. It's capable of taking it back, which makes it kind of like a base. Same thing with a base. A base takes in a proton from somewhere else. So that's what bases do. They accept protons. But then it's always capable of giving that proton away again. Right? So that makes it, if it's given it away, that makes it kind of acid-like. So let's look at an example here. All right? Our first example. I know HCl is an acid. That's hydrochloric acid. Right? And we're going to combine that with water. So here's water here. And what we'll get is H3O plus and Cl negative. All right. So what happens when we drop hydrochloric acid in water? It dissociates. Remember we said water was polar, right? We took a look at water in a previous lecture, the solubility lecture, and we said this end slightly positive, this end slightly negative. And so when it comes into, comes into contact with ionic compounds, the negative oxygen says to the positive hydrogen, how you doing, right? Remember that? And these hydrogens, which are slightly positive, go up to the negative chlorine. They're like, hey, how you doing, right? Opposite charges attract. So what happens here is when we dump the hydrochloric acid, a pretty strong acid, in water, it dissociates. It falls apart. So dissociation means it does this. It separates into the ions. And you can see here what happens is the proton here, because H pluses are now protons, it comes and joins onto the water. So the acid gave off the proton, because that's what acids do, and the base accepts it. H2O becomes H3O because it picks up this. So this ends up going and joining onto that. So in a way, what basically happens, is that the acid, HCl, acts as the acid, and the water acts as a base because it accepts that proton. Now, let's go over here and take a look at this. So this is called the hydronium. I'll write that in here at the top because we are going to have to know about that in a future lecture. So this is the hydronium ion, this H3O plus, right? This is just simply a chloride ion. We've seen those before, right? It's a chlorine ion, but they call it a chloride ion. Now, the hydronium ion here, if we look at it, the hydronium ion, right? Water acted like a base. It accepted the proton. It formed this thing. This can easily revert back into water. So H3O can go back and become H2O. But how does it have to do that? Well, it would have to get rid of that proton that it picked up. And so it means the base and what the base became can now act like an acid and give away the H and go back to being the base. Right? So this has almost like acidic properties now where that extra H that's on it can be given off. And this will go back to H2O. Right? This thing right here, if I look at chlorine, it came from the acid, right? It was part of the acid. There's my Cl there. The acid donated the proton or gave it away. Water picked it up. But this is a remnant of an acid, but now it can act like a base because if there is a proton in the area, these two charges can attract and this can accept a proton, even though it was originally part of an acid, which is a proton donor. The leftovers from it can now be a proton acceptor. So we have terms for this, all right? And I'll underline them here. So in this, oh, I erased half of my acid here. There's my acid, right? This is my base. The acid, its leftovers are right here. This can accept a proton. It's negative, a proton's positive. I can add a proton to this. This is a proton acceptor. This is called my conjugate. I'm going to erase that little arrowhead there. Give me a little bit more room. This is my conjugate base. All right? The acid makes the conjugate base. Every acid can form a base. It's leftovers anyway after the reaction takes place. Every base can form an acid. So the water accepted the proton, but now it's capable of giving that proton off and donating it, so the base forms the conjugate acid. All right? Again, I'll go through that slowly because I think this is the trickiest part of this lecture. So, hydrochloric acid, water. Water is capable of acting like a base here, so the acid dissociates. This H goes onto this and forms H3O. Because this gave away its proton, the H+, this is my acid. Acids donate or give off protons. The leftovers of that acid, once it gives away its proton, is just the Cl-. But the Cl- can attract a proton because it's negative and protons are positive. So this becomes like a base. It can accept an H+. So my acid, its leftovers, are the conjugate base. Look at my base. Water in this example is my base. Water accepts this proton from the acid. When this falls apart, that H goes onto here and forms H3O. Because it's accepted a proton, it's a base. Now what did it form? It formed this hydronium, this H3O. The hydronium can go back into water. But to do that, it has to give off the proton. And when you give off or donate protons, you're an acid. So this is the conjugate acid formed from this base. So I hope that's clear. I have another example here, and we'll go over it. We'll take a look at it. Here's our ammonia, right? I'm going to erase this. Pause the video. Go back and pause the video if you needed to get that down or make sense of it. Remember, you can always add or write in little notes along with my notes. So let's take a look at this next example here. Ammonia and water. And we've got OH negative and NH4. Do it nice. NH4 positive. All right. And then we've got plus yields plus. All right. So here's another example. All right. Here's ammonia. Let's take a look at what happens here. I've got ammonia and water, and in the aftermath I've got OH. I know the O can only come from the water, so the water looks like it lost a proton because it's H2O, but now it's just H and O. And if I look at ammonia, it was NH3, and now it's NH4. So what happened was one of these H's joined onto this, right? Just by looking at the equation. This accepted a proton and went from NH3 to NH4. That means this is a base. And that proton, that hydrogen ion, came from the water. The water is an acid. All right? And so if we look here, let's use our rules. Every base can form an acid. So this is my conjugate acid. Why is it a conjugate acid? Because NH4 could get rid of that extra proton. It could give off that extra proton and go back to being NH3. If you give off protons, you're an acid. The base forms the acid. And here is my acid. The water gave off the hydrogen, and what was left over was this. This is my conjugate base. Every acid forms a base. This now has a negative charge. If a proton comes along, it could combine with this, so this will accept that proton, take it on board, and form water again. All right? The easy way to remember it is once you identify your base, its leftovers or whatever it forms has to form an acid. Base becomes acid. acid becomes base. So always take, same thing here. I know HCl is an acid, right? I know water, in this case, is the base. And look, this over here has to be my conjugate base, because oh, sorry, not that. Conjugate acid. I wrote the same thing as below. This is my conjugate acid, and this is my conjugate base. All right? The base, what does it form or leave behind? This thing. The base becomes the acid. What does the acid form or leave behind? This thing. That's my base. Acid forms base, base forms acid. I should draw that in red because then it will kind of match up with what's on the other side here. So the acid forms the conjugate base, and the base forms the conjugate acid. All right? One interesting thing here. Look at water. Right? Hydrochloric acid is always going to make an acid of itself. See what I did there? Anyway, ammonia will always be a base. Hydrochloric acid will always be an acid. But water, with the acid, water took on the role of the base. And with the base, water took on the role of the acid. And that's because water, H2O, is amphoteric. And what amphoteric means, it can be an acid or a base. It depends on the other thing, right? If water's with an acid, it says, yeah, I'm easy, I'll be the base. If water's with a base, it says, yeah, sure, I'll go along, I'll be the acid. So it's amphoteric. Think of an amphibian. Half water, half land, right? Like frogs and stuff like that. It can be one or the other. It's not strictly water-based, it's not strictly land-based, it's both. It's not strictly an acid, it's not strictly a base. It can act as either one, depending on what the other thing is. All right? So amphoteric, that's water. Now, pause the video, get that down if you need to. And I'm going to talk about how we know acids are strong or weak. Same with bases. How do we tell if they're strong or weak? All right. I'll do this in black here. So strong, and this applies to both acids and bases. Strong versus weak. How do we know an acid is a strong acid and will do, corrode metal really quickly or do a lot of damage to body tissue versus a weak acid, which won't do a lot of damage and may not corrode metal all that much at all, right? So how do we know strong versus weak? That V is not doing it for me. Well, this marker's leaking. Let me give this another try. Uh-oh. Disaster in the lecture. So, strong versus weak, right? How do we tell the difference between the two? What it comes down to is something called dissociation. All right? Dissociation, if you remember, is basically, I'm going to have to get a marker. This one is really leaking out the fluid. Dissociation is basically falling apart. Right? We just looked at it with the hydrochloric acid. With the hydrochloric acid, if I drop that in water, it does this. The H pluses will separate from the Cl minuses. Right? If I put NaF in water, it will dissociate, which means it'll form Na plus and F minuses. So dissociation is basically the opposite of association. An association is a group of people together. If they dissociate, it means that they came apart. I'm going to have to see what's going on with that marker. Not pleased about that, but I guess there's nothing we can do. Look at it later. So dissociation means to fall apart. Now, a strong acid or a strong base. A strong acid or base completely dissociates. 100% it's fallen out all over the place, right? So hydrochloric acid can be pretty strong, which means it's separating. So I drop these into water, boom, separate, boom, separate, boom, separate. None of them are staying together. They're all falling apart. And what that does is it's going to fill the water full of what? H pluses, because when an acid falls apart, the H pluses are given off. And an acid is identified as a proton or H plus donor. So a strong acid is giving off protons left and right. They're walking down the hallway firing off protons to everybody, like Oprah, right? A proton for you and a proton for you, and you get a proton and you get a proton, right? Same thing with a base. A base is going to dissociate, accept the proton, and there's going to be OHs everywhere, right? I'll show you that in a second. So when this happens, it's known as this dissociation. It's called ionization because we're forming ions, right? The dissociation of an ionic compound forms ions. So it's also known as ionization. Now, a weak one, if it's weak, it only partially dissociates. So not the whole thing doesn't, right? So a couple of good examples here, right? Sulfuric acid, that'll dissociate like crazy. What I'll get is a couple of protons and the SO4, like that, right? When it dissociates. If I look at carbonic acid is a weak acid, right? Some carbonic acids it'll form H pluses and CO3s. But some, when they fall in water, they stay together. Partially means only some dissociate or fall apart. So when I dump this in there, they're all like, woohoo, they're jumping apart left and right. I dump this in water and some of them, hey, let's separate. Others are like, no, I'm staying together, right? We're not going to dissociate. We're weak. We're partially dissociating. I'll stay together. You fall apart, right? A strong one, everybody's falling apart. Same thing with bases. Bases, when you put them in water, if it's a strong base, like LiOH, it's going to dissociate and form Li ions and OH ions. It's a strong base. So it dissociates. If I drop this in the water, they're separating left and right. All of them. Right? The weak one only partially dissociates. So the weak one, again, will kind of be like our carbonic acid here. Some will stay together. Some will fall apart. Right? So we look here at this diagram. Here's a strong acid. And now, if you blow this up on your iPad or computer, you'll see each of these little molecules that's coming out of the eyedropper here has a red circle and a white circle. There's my acid there. We drop it into water and look what happens. All the red and white circles separate. None of them are still together anymore. They're together in here. They're together as they fall, but when they make contact, they separate. They dissociate. In the strong acid, all of them fall apart. Look at the weak acid, like carbonic acid. They're together here, the red and white circles. They're together. They hit the water. Some of them, like this one and this one down here, have dissociated. Some of them, though, like these guys right here, have stayed together. All right? So they only partially dissociated. Now, if you're an acid and your whole identity is giving off protons, there's way more protons being given off here than here. Here are protons. Every time this falls apart, it makes protons. That makes this a wicked acid. It's awesome at being an acid. This one, well, yeah, it made some, but not all. So this is a weak acid. Yeah, you're still an acid, but this one's way better at doing the job that an acid does. And it works the same way for bases, right? Some bases will give off and form tons of hydrogen ions, right? they'll accept tons of protons, right? Your whole identity is accepting protons. So if you accept a ton of protons in water, then you're a wicked base. You're awesome. If you only take some protons and because other parts of you stayed together and you wouldn't dissociate, then you're a weak base. Because your identity is to accept protons. And the more you do that, the better you are. And you have to dissociate to do the donating or to do the accepting. Anyway, that's the end of the lecture. Professor Frink has told us. Hope everything was crystal clear. If there's any questions, comments, or concerns, reach out to me through the comment section below this video, or if you're one of my students, through the EDSB wall. Anyway, I'll talk to you soon. Bye-bye.